In this video, we're going to talk about how do we compute an inverse matrix? How do we find a formula for A inverse? So first look at the case where n equals 2. So if I have a matrix A that has 2 rows and 2 columns. Okay, so I just wrote the entries as A as being A, B, C, and D. So this matrix is invertible if and only if. So here's our symbol for if and only if. So it turns out it's invertible if and only if A times D minus B times C is not equal to, 0. So this expression A times D minus B times C, we see it often actually, it turns out, with 2 by 2 matrices. And it has a special name. It's called the determinant of A. Let me give myself a little bit more room here. Okay, so this is called the determinant of A. So that's my notation for the determinant. So the determinant of A. So we'll talk about the determinant more in detail. We'll see this in chapter 3. So for right now, I'm just going to introduce the term to you guys, but we'll talk about it a whole lot more in detail in chapter 3. So when the determinant of this matrix is not 0, it is invertible, it turns out. And in that case, then the formula for the inverse is we have 1 over the determinant AD minus BC. That's going to be a constant in front of my matrix. And my matrix is going to look like D here and A here, so they switch spots on the diagonal. And then the B and the C both become negative. So it turns out that this is a formula for the inverse of a 2 by 2 matrix. And it's not hard to check why this formula works. Like I could multiply A inverse by A and check to see that I get the identity. One reality check is, notice that when the determinant doesn't equal 0, so when this expression doesn't equal 0, that's good in terms of our formula because that means that this denominator of this fraction is not going to be 0. If it was equal to 0, this denominator would be 0, and that would make this undefined. From a more conceptual standpoint, it turns out that when this determinant, A times D minus B times C, equals 0, the columns of our matrix are going to be multiples of each other. And if they're multiples of each other, they're not linearly independent, and then my matrix is not going to be invertible. Okay, so let's do an example. So let's compute A inverse if A is the following matrix. Okay, so let's solve this. So A inverse, so the formula for that is it's going to be 1 over this determinant expression. So A is 1, D is 4, minus B is 3, and C is 1. And then times, and then within the matrix, we switch the 4 and the 1. And then the 3 and this other one are in the same spots, but we just put negatives in front of both of them. In simplifying this, so my determinant here ends up just being equal to 1, so I'll just have a 1 in front. So that doesn't affect my matrix at all. I'm just left with 4, negative 3, negative 1, 1. And that's my formula for my inverse. And it's easy to check if we were to multiply this matrix by A, either on the left or on the right, I'm going to get the identity. Okay, so next I want to talk about how do we find the inverse if we have a bigger matrix. So when n is greater than 2, the formula for finding the inverse is way more complicated. I can write down a formula like this, it's just a lot more complicated. So instead, we have an algorithm to find the inverse. So an algorithm is a systematic procedure. Okay, so I want to motivate what that algorithm is a little bit. So the invertible matrix theorem that we talked about in the last video, part of that theorem says that a matrix A, when it's n by n, is invertible if and only if A is row equivalent to that identity matrix. If and only if A is row equivalent to that identity matrix. Symbolically, we'd write A and then this squiggly line that refers to is equivalent to IN. So now here is a key theorem that's going to motivate our algorithm for finding the inverse. If A is invertible, then it turns out if I take A, I put it in a matrix, and I augment it with another matrix, so not just a column vector, I augment it with an identity matrix, and then I row reduce this augmented matrix. Well, because A is invertible, the A on the left-hand side should row reduce to that identity. And when I do those steps, the identity, so the thing that I have on the right-hand side of the augmented bar, it turns out that that becomes A inverse after I do my row reduction. Okay, so this whole thing is my reduced echelon form. Okay, so now we're ready to state the algorithm, so the key steps. But it's based off of this theorem right here. So there are 3 key steps to finding a formula for the inverse matrix. So the first is we write A augmented with the identity matrix, augmented with IN. The second step is we put this in RREF form, so the reduced row echelon form. And when we do that, as long as my matrix A is invertible, it should row reduce to that identity, to IN. And then the right-hand side is going to row reduce to something, to some matrix. Let me just call it B. And then this theorem tells me that, when I do this row reduction, then that matrix B that I have on the right-hand side of this augmented bar is the inverse of A. So the proof of this algorithm, in particular the proof of this theorem that I talked about, involves the use of something called an elementary matrix, which I haven't talked about, but they do talk about in your textbook, in case you guys are curious and want to learn more about, well, where does this come from? Why is this result true? I'm going to focus our time more on using this algorithm. Okay, so let's do an example. Okay, so here is the example. So part A says, we have this matrix. First off, is it invertible? And if it is, if so, then find its inverse. Okay, so let's solve this. So what I do first, according to my algorithm, is I go ahead and write my matrix 1 3 0 2 1 1 0 1 1. So I put that on the left-hand side of the augmented bar, and on the right-hand side I write the identity. So 1 0 0 0 1 0 0 0 1. So we know from the invertible matrix theorem that if I want to check if my matrix is invertible first, I would just row reduce it and check to see, for example, if there's a pivot in every single row and every single column. And if that's the case, it's invertible. So I could decide to do that first, like not write this whole augmented part and just do the left-hand side. But the advantage of doing this together and putting the augmented part on the right is, at some point, I'll discover whether the left-hand side has a pivot in every single row and every single column. And if it does, awesome. I keep going and I row reduce it fully to get it in RREF form. If it doesn't, I get to stop anyways, because then I can say, oh, my matrix is not invertible. Okay, so let's begin our row operations on this. So I need to make this 2 underneath this 1 up here, a 0. So I'll do that by doing -2 row 1 added to row 2. And then we'll substitute that into row 2. So doing this, the first row stays the same, 1 3 0, augmented with 1 0 0. The third row stays the same, 0 1 1, augmented with 0 0 0 1, 0 0 1. But the second row is going to change. We're going to get a 0 here, and then -2 times 3 is -6, added to 1 is -5. And then -2 times 0 0, added to 1 is 1. On the right-hand side, I'll get -2 times 1 is -2, added to the 0 is -2, and then I'll have a 1, and then I'll have a 0. So next what I'd like to do is, I'd like to have, where this spot is, I'd like to have a 0 there, where this 1 is in the third row. My computation is going to be easier if I switch the second row and the third row, and I put the 1 where the -5 is. Okay, so if I do that, let's switch the second row and the third row, because it's going to make my computation easier. If I don't do this, to sort of zero out this 1 right here, I would have to multiply row 2 by a fraction and add it to the third row. And usually if I can avoid having to do that, it's nicer. So switching these two rows will let me avoid it. So the first row is still 1, 3, 0, 1, 0, 0. Now the second row is 0, 1, 1, 0, 0, 1. And the third row is 0, negative 5, 1, negative 2, 1, 0. Okay, so now I can go ahead and zero out this negative 5. And I'll do that by taking 5 times row 2 and adding it to row 3 and inserting that into row 3. So doing that, my first two rows stay the same. So 1, 3, 0, augmented with 1, 0, 0. Second row is also the same, 0, 1, 1, augmented with 0, 0, 1. But the third row changes. I'll have 0, 0. 5 times the 1 is 5, added to the 1 is 6. 5 times 0, 0, added to negative 2, that doesn't change it. That's negative 2. The next number is still 1. And then 5 times this 1 is 5, added to this 0 is going to be 5. So at this point, I can see the pivots on the left-hand side. I see that this 1 is a pivot, this 1 is a pivot, this 6 is a pivot. So I can answer the first part of the question about whether my matrix is invertible. There's a pivot in every single row and column of the left-hand side. So that's in my original matrix. So my matrix is invertible. It's square, and there are pivots in each column and row. Remember, if my matrix is square and there are pivots in each column, there are also pivots in each row, and vice versa. Okay, so I've answered the first part. It is invertible. Next, if it is invertible, keep going and find the inverse. Okay, so I need to put the left-hand side, that's all of this, into RREF form. It should transform, it should row reduce to that identity. Okay, so the next thing I would do is, two of my pivots are already 1, but the 6 isn't. So at this point I have to get, I have to roll up my sleeves a little bit and introduce some fractions, which is okay. I'll multiply that third row by 1/6 and insert that into the third row. So doing this, the first two rows stay the same. So let me just fill those in quickly. Okay, so I've gone ahead and filled in those first two rows. They did not change. But the third row, I'm multiplying by 1/6. So I'll get 0, 0, and then I'll get 1. So negative 2 times 1/6 is... I'll go ahead and simplify it. So negative 2 times 1/6 is negative 1/3. 1 times a 6th is 1/6. And then 5 times 1/6 is 5/6. So I got some fractions, but that's okay. We can handle fractions. Okay, so I've made all the pivots 1s. Now I need to make the things above the pivots become 0. So we're starting with the bottom right. So I need to make this 1 become a 0 next. So I'll do that by doing row 2 minus row 3 and inserting that into row 2. When I do that, the first and the third rows don't change, so I'll still have 1, 3, 0, augmented with 1, 0, 0. Third row is still the same, 0, 0, 1, and then negative 1/3, 1/6, 5/6. But the second row is going to change. When I do the second one minus the third one, I'll get 0. Whoops. Sorry, that's just shifted over a little bit. Okay, so I'll have 1, 1, 0, 1 minus 1 is 0. 0 minus negative 1/3, positive 1/3. 0 minus 1/6 is negative 1/6. And then 1 minus 5/6 is 1/6. Okay, so at this point, I've made everything above this 1 down here, a 0. So I move up to the next pivot above it. So that's this next one in row 2. I need to make the things above that become 0. So that's this 3. So I'll do that with one more row operation. I'm actually one row operation away from fully row reducing this. I'll do negative 3 row 2 added to row 1 and substitute that in to row 1. Okay, so the second and third rows stay the same. 0, 1, 0, augmented with 1/3, negative 1/6, and whoops, positive 1/6, positive 1/6. Third row still the same, 0, 0, 1, negative 1/3, positive 1/6, and positive 5/6. So when I do negative 3 row 2 added to row 1, so I'll get a 1 there, a 0 there, a 0 there, and that part is not bad. Okay, so negative 3 multiplied to 1/3 gives me negative 1. And if I add that to 1, I get 0. So then negative 3 multiplied by negative 1/6 is positive 1/2. And if I add that to the 0, I'll get positive 1/2. Negative 3 multiplied by this 1/6 is negative 1/2. And negative 1/2 added to 0 is negative 1/2. Okay, so at this point we've row reduced our whole augmented system. We've made the left-hand side become the identity. The right-hand side, when we do this, is the inverse. So our inverse, writing it out explicitly, A inverse, is 0, 1/2, negative 1/2. Let me write out the other rows more quickly. Okay, so the other rows I've gone ahead and just filled in, but that's the formula for our inverse. So that's how we use this algorithm by row reducing to get a formula for the inverse, to figure out what it is. Okay, so let's take a look at part B of this example and see how can we use the inverse. Why is this even useful to us? So let's solve this linear system using part A. So I don't want to do this, for example, by forming an augmented matrix. I want to use part A to help me. Okay, so I want to do this without any sort of row operation. Okay, so I have this system of equations. The first thing I'll do is I will go ahead and write this equation in matrix form. Okay, so if we do this, the left-hand side becomes 1, 3, 0, and then I'll have 2, 1, 1. I'm just taking the coefficients of these variables. Then I have 0, 1, 1. So that's going to be multiplied by the vector x. So note that the vector x is the vector that has x1, x2, and x3 in this case. We have 3 variables as the entries. And on the right-hand side, this equals the vector 0, 12, and 6. So 0, 12, and 6. And let me go ahead and space that out a little bit more. 0, 12, 6. Let's space this out a little bit more. So why it's useful for me to know the inverse is this matrix right here is A. I know that when I multiply A by A inverse, it gives me the identity. So if I multiply this on the left-hand side by the inverse, well, if I do that on one side of my equation, I also have to do it on the other side. So I also have to multiply this vector by A inverse. And I have to stay consistent with which side I multiply on. So I've chosen the left-hand side to multiply the A inverse on. And I wanted to do that so I could put the A inverse right next to the A. So A inverse times A is the identity. So we get the identity. We still have that vector x. And on the right-hand side, we have A inverse. And remember, the formula for A inverse was we had 0, 1/2, negative 1/2. We had 1/3, negative 1/6. And then I think we had positive 1/6, negative 1/3, positive 1/6, and I think positive 5/6. So that was the formula for A inverse. And then we have times the vector 0, 12, 6. Okay. Ooh. So the identity times anything is just that anything. So the identity times x is just x. And now on the right-hand side, I just have to multiply this matrix times this vector. And that's not hard to do. If we work out what it is, what we'll get is, so if I do the row column thing, I'll get 0 times 0, which is 0. 1/2 times 12, which is 6, so I add 6. And then negative 1/2 times 6 is negative 3, so I'll add negative 3, and that's my first entry. If I do the same type of thing for the other rows, I'll get 0 minus 2. I'm going to go more quickly, plus 1. For the next entry, we'd get 0 plus 2 plus 5. And simplifying this, we get 3 -1, 7. So why this is nice is, notice that I needed to solve this system of equations, but I did it without any sort of row operations. That's why having the inverse was really nice. So knowing the inverse makes solving a matrix equation a lot quicker because I get to avoid row operations.